Hi, today we're looking at electric potential due to a point charge. Now, our electric potential can be calculated utilizing the following formula. V equals kq over R, where V is our electric potential measured in volts. Q is the charge of object producing the potential measured in coulombs. And R is the distance from the charge producing the potential measured in meters. Now, our electric potential is a scalar quantity, meaning it does not have direction, and it is purely magnitude. Now, we can have more than one electric potential, so that brings us to potential difference. So we can use the following formula to calculate the potential difference between 2 points in space. So on our formula sheet, we have change in PE equals QVB. So that's our change in potential energy is equal to our charge times our potential difference between points B and A. Now, rearranging this, we get our potential difference between B and A is equal to our change in potential energy divided by our charge. We'll redefine some variables, and we can say that VBA is equal to our electric potential at B minus our electric potential of A, which is equal to our change in potential energy, which is just equal to our work as we move our charge between B and A divided by our charge. So we'll look at an example of this. We want to know what the electric potential is at point P, and we've got two charges. We have one that's 2 times 10 to the negative 6 coulombs. That's 7 meters away from a point, and another that has the same charge, but it's just 4 meters away from our point. So we'll look at one that's 7 meters away first. So we know its charge, we know its distance. We'll solve for the electric potential due to it. So that's kq over R. Substitute our values in, and we get that it has an electric potential of 2,571 volts. We'll do the same thing with charge 2. So we'll utilize the exact same formula, and we have 4,500 volts. Now, if this was electrostatic forces, we'd have to combine these using Pythagoras because forces is a vector. Electric potential is not a vector, it's a scalar, so we just combine these two electric potentials by adding them. So we've got our electric potential at that location is equal to the potential from one plus the potential from the second one, giving us, when rounded to appropriate sig figs, an electric potential of 7,100 volts. Okay, next example. How much work is done against an electric field produced by a 7.5 microcoulomb charged object when a 0.05 microcoulomb charge is moved from 5 centimeters to 2 centimeters away? So we'll start by writing out some basic values we're given. So our larger charge that's producing our field is our 7.5 times 10 to the negative 6 coulombs. Our charge that's being moved is 5 times 10 to the negative 8 coulombs. And we have a starting distance of 0.05 meters and an ending distance of 0.02 meters. So utilizing our formula sheet, I would be using our change in potential energy is equal to our charge times our potential difference. Now, our potential difference is essentially our potential difference at B minus our potential difference at A. And our change in potential energy can be described as our work. Now we can substitute in formulas for our potential differences at each of those locations. And what you'll notice is inside our brackets, both of our fractions have a kq1, so we can factor that out. At this point, substitute our values in. And we get a work of 0.10125 joules, which rounding to appropriate sig figs is 0.1 joule.